Oh, yeah, your list. Yeah.
Chapter 14 has all the solutions.
What?
Chapter 14 has all the solutions. Solution chemistry. Yes. Raylan didn't find that funny at all. Okay.
Not
So,
funny, Libby. I want to learn.
I know,
Not
I
your
know.
jokes.
So concentration.
I was just gonna say that.
Hey guys, let's concentrate a bit.
Is a measure of how much solute, and yesterday you discovered what solute was. That's the stuff that's dissolved in a solvent. And if you think back to chapter 3, we had a lot of examples of that. One of the ones that I used a lot was Kool-Aid, where you have your sugar and you have your Kool-Aid powder, and then you have your water. So your sugar and your Kool-Aid powder is your solute, and then the water is going to be the solvent. We can express this concentration in 5 different ways because you can change the amount of solute. Let's say that you wanted that Kool-Aid to be really, really sugary. You could add more than the 1 cup of sugar that recipe calls for. Okay. Or if you didn't want it to be as sugary, you could add a half a cup in. Okay. You could add in 2 packets of the Kool-Aid mix instead of 1. So that would change your solute. You could also change your solvent. You could add in the regular amounts of stuff, 1 package, and you could add in twice as much water, or you could add in half as much water, and that would change the concentration of this. And we could express that in different ways. So first of all, you need to have some decent vocabulary with this. You need to know that the solute is what is being dissolved in the solvent. And when those 2 things are dissolved together, it makes a solution. The mass of the solution then is your solute mass plus your solvent mass. So you add these 2 things together, and that's going to give you your mass of your solution. Then you multiply it by 100 to give you a percent. So for a solid dissolved in a liquid, this is typically what this is used for. You have the mass of the solute divided by the mass of the solution times 100. So this is part. You're looking at a part divided by a whole. So the same type of percentage that we've been doing all year long. Yeah, like percent composition, we did percent yield, we did, I mean, there's just been lots of different times where we've done percentages. Yep. In order to maintain sodium chloride concentration similar to salt water, an aquarium must contain 3.6 grams per 100 grams of water. What is the percent mass of NaCl in the solution? So look at this. Is this 2 parts, or is this a part and a whole? 2 parts. So to get the whole on the bottom, we have to add them together. So that's going to be 3.6 divided by 103.6 times 100. Is that right?
No, 4.7.
3.47%? Okay. I'll trust you guys on that. All right, so there's your answer. Easy enough? The problem is that you have to read, like, be careful to kind of dissect this and make sure that, you know, you're seeing, okay, is this a part and a part? Or sometimes they'll give you a part and the whole thing. And so that's where you've got to be a little bit more careful with kind of reading what the problem's saying. All right. The next one is done the same way. This is just volume instead of mass. This is volume. And the reason why sometimes they like to use mass instead of volume is because volume changes. Volume changes for some of these things based on temperature. And you guys saw that in the last chapter. So in certain cases, this becomes more beneficial to work with than this. All right, ratio of volume of a solute over volume of the solution. And again, same terms here, solute, solution. So here, they're giving you your percent. So if we want to work with this, we want to get it out of percent form, which gets us out of the 100 here. Okay, So we're going to divide this by 100. So we're going to start out with 0.7 equals, and they've given us, they want to do volume of the water. They've given us 100 mils. So that's our total on the bottom is 100 milliliters. And we want to go X here. So we're going to solve for X. What is X? 70. 70 what? Milliliters. 70 milliliters of what? Right, isopropyl alcohol. But they didn't want to know that. What did they want to know?
Water.
How much water. So if we know that this is one of the parts and there's only two parts there, water and isopropyl, that means that the water has to be 30 milliliters. The other way that you could have approached this is you could have said, okay, if this is 70%, the water is 30%, and you could have started this out as 30, ended up with 30 here, and then that would have been your water. Does that make sense? Okay. So there's a couple of different ways to approach it. All right. The next one here is molarity. This is by far, unquestionably, the most important one that you understand, especially if you are going into AP Chem. We use this all the time. So remember when you have seen, like when you've gotten acid in here and it said 6 and it had a big M and it said HCl, okay? And you're always asking, is this the right stuff? What is this M business? Okay, this M business that you've been seeing all along is the fact that you've been using a 6 molar hydrochloric acid as opposed to a 1 molar hydrochloric acid. Okay, so this is 6 times more concentrated than this. That's why I've said with the 6 molar acid, if you get it on your skin, make sure you wash it off right away, or after time, it's going to start, eating away at your hands. Hi.
So what's the solvent then?
The solvent, so you have HCl, that you have your acid, and then you have your water is your solvent.
Yeah, it's always water.
So when we get this in, we get in 12 molar. Okay. And this is the HCl, hydrochloric, is the solute, and then you add water to it. So when we get it in from the manufacturer, we get in 12 molar. And then I have to go through a process, and I'm going to explain what that process is. I have to go through a process to dilute this down into whatever concentration we need for a particular lab. So some labs, like your one that you did with the baking soda with the balloon where you put it down, we didn't need a very high concentration for that one. But your penny lab, we did. We needed a much higher concentration. So I end up looking, and some of that comes down to limiting reactants too. Like if you don't have a high enough concentration, like if we would have done a 1 molar, it wouldn't have been able to, it wouldn't have had the right molarity. It wouldn't have had enough of the HCl in there, enough of the hydrogen ions to be able to react with all of the zinc. So I have to start you out with a high enough molarity in order for that to happen. Yeah.
Will we have another balloon lab this year?
No.
We're done.
All right. So
I'm taking L on today.
So to figure out molarity, what you have to do is you have to know your moles of your solute. And remember, if you're given grams, you divide grams by the molar mass to get moles. Okay, so you have to have moles here. And then this is liters of solution. And remember, for every 1,000 milliliters, you have 1 liter. Okay, so if they give you 750 milliliters, you're going to divide by 1,000, and that's going to give you 0.750 liters. So this has to be in liters of solution in order for this to work. Okay. Any questions about any of that material? Anything that I've thrown at you so far? All right. So we have 105 milliliters. So I've got to back my decimal up 3 spots. Remember, if you just take this and move it 3 spots, that's the same as dividing by 1,000. So if I move that 3 spots, that becomes 0.1005. That is 5.1 grams of glucose. So I'm going to take 510 grams. I'm going to divide it by the molar mass of glucose, which you can calculate if you'd like, but I can just tell you it's 180.
Oh, I did it right.
I have that one memorized. And that ends up being, I needed to, divide that. So, that's right. So 0.0283. I'm going to divide these out then, and that ends up being a 0.282 molar solution.
That's what I put on my paper. Okay. Preparing a molar solution.
Does that make sense?
See?
So what you have to do if you wanted to prepare like one sucrose.
No, we can't do it anymore. These are race. Actually, I do remember what's on the list, so it's fine.
As long as we do the fire blanket party, it's good.
Fire blanket what?
All right, so sucrose. Let me look up the formula for sucrose.
Look at this. If you were to bring
12, 22.
acid to this side of
Okay.
the bowl, have that for next.
So we're trying to figure out how to make a 1 liter, okay, 1 liter, 1.5 molar solution of sucrose. So sucrose is C12H22O11 for its molecular formula, okay? We know that there's 1.5 moles of sucrose for every 1 liter of water, right?
Right.
So I need to find the molar mass of this guy. 12 plus 11 plus 11. 166 plus, I need to take oxygen, 11 times 16. Okay, so 342. All right. So I'm going to add, I know how many grams that is. That ends up being 513 grams. The molar mass of this is 342. So if I take 1.5 times 342, that ends up being 513 grams. Okay. And what you're going to do, we're going to pretend that this is a 1 liter. It's not, but we're going to pretend. You're going to take this container. This is called a volumetric flask. This container is only good for 1 volume measurement, and that is it. Okay. So you add your sucrose into here, and then you add water up to the top. You can't just add 1 liter of water in. Okay, remember we had that video, the volume of mixing, where the girl had the alcohol that she mixed with the water. Do you remember that video? And yes, the one with the poor quality. It was a Bill Nye one.
Yeah, you can't listen.
It wasn't stellar. Yeah, it's really annoying. Yes.
Yeah.
Okay.
Okay, I remember.
But remember how when she mixed those two things together, it came out less than the volume you would have expected to. It wasn't just additive. When you added them together, it, the particles, some of them went in between other ones and your volume decreased. So to do these measurements, you have to have a very precise piece of instrumentation. And you guys next week are going to be doing a lab where you have 100 milliliter volumetric flasks. So you're going to find the mass of the powder that you have to have in, and every lab group is going to be different. Okay. So you're going to find the mass of the powder, you're going to put it in your volumetric flask, and then you're going to mix it up until the meniscus forms at the base of this etched line. This etched line is on here. What they did was at a certain temperature, and it'll say usually on the flask, 20 degrees Celsius. At 20 degrees Celsius, you will have 500 milliliters of liquid. But again, it'll change with temperature. Yeah.
So the concentration is based on like how much of the solute you put
Yep.
in there?
How much solute is in there? That's your concentration, because that's your moles over your liters of solution.
Okay.
So you'll end up putting in just slightly less than 1 liter of water. If you added a whole liter in there, it would actually be less concentrated. It would be more dilute, is what they call that. So you have concentrated and dilute. Those are the two extremes. All right. So you're going to pour that into the volumetric flask, add your water to that calibration mark, and now you've got 1 liter of that solution, and it should be 1.5 milliliter sucrose. Okay. Usually solutions, oh, what did I want there? Oh, diluting. So they come in very concentrated. They come in standard molarities. Those are called stock solutions. And the reason why I think that they call them stock solutions is because that's what you have in your stockpile. Okay, when you have, like in my back room, I have a stockpile of stuff, right? They call it a stockpile. You've heard that term before, maybe. Like, they talk about stockpile of ammunitions and stockpile. So in my inventory, so to speak, I've got these stock solutions. So typically your hydrochloric will come in at 12 molar. Your sulfuric will come in at 18 molar. Your phosphoric, I believe, comes in at like 4, or maybe it's nitric, comes in at 14.3. I can't remember which one's which. So they come in at different molarities. And what we have to, the nice thing about this, the reason why you want them to come in at these high molarities is because I can dilute this down to any molarity I want, but I can't go backwards. So if I got hydrochloric in at 1 molar, I can only go down from that. I wouldn't be able to go back up and get 12 molar. Does that make sense? But with 12 molar, I can make so many different concentrations. I can make any variation I want that's less molarity than this, which is kind of nice, right? That makes sense? All right. So we prepare a less concentrated solution by diluting the stock solution, and that's by adding more solvent particles. Okay, so we can rearrange, since the number of solute particles doesn't change, we can rearrange the equation for molarity to solve for a solute. So the moles of solute do not change because we're just adding in solvent. So the moles of our stock solution equal the moles of our solute. We can rearrange that molarity equation, since we know that moles over liters equal molarity, right? So if I wanted to solve for moles, what would I do? Right, moles equals molarity times liters. Everybody buy that? Okay. This doesn't change. My moles of my concentrated form or my stock form equal my moles of my dilute form. Okay. So that means that the molarity of the first equals the times volume equals the molarity of the second times its volume. See what I did there?
Sure.
Okay. And this is probably one of the most common formulas that I use throughout the year to get your labs prepared for you. So let's see, this looks like it had a decimal drop out of here. So we're going to put a point there. Why that got missed. But it just makes sense. All right. So what volume in milliliters? Now, the nice thing about this equation is, as opposed to this one has to be in liters. Okay. The nice thing about this one is it can stay in milliliters. But they have it in liters, so we'll just stick with that. All right. So our stock solution, they're asking us how much stock we need. So we're trying to solve for this guy right here. No, we're not. I lied. Lippy lied. We're trying to solve for this. We know the molarity of our stock solution. The molarity of our stock solution is 2. We're solving, we want to know how much of that we need to add to our volumetric flask. So our volumetric flask is sitting over here. It has its little etched line on it right here. And they want to know how much of this 2 molar we need to add in so that we can end up at 0.3 molar. This is going to equal 0.3 molar times 0.5 liters. So I solve for that. I multiply these 2 things together and divide by 2. 3 times 0.5, 0.15 divided by 2. So that's 0.075 liters. I don't have anything that measures in liters, though. I have it that measures in milliliters. So how many is this in milliliters? Yep, this is 75 milliliters. So I'm going to have my 2 molar. I'm going to add 75 milliliters into here. And then I'm going to fill the rest of this up with water. That makes sense how you do those? This is your lab next week, so you need to make sure you know how to do this.
What? Oh, that?
Yep, that's the second part of your lab. The first part of your lab is this guy. So you're going to take this, and then you're going to take some of this, and you're going to dilute it down using this equation.
Okay. This.
Okay? All right, solution concentration then. The volume of a solution may change with temperature. So here in town, we've got a couple chemical plants. One of them's down by the river, kind of off of, just a little off of Center Avenue. And my guess, I haven't really talked to them lately, but my guess is that they deal more in molality than they do in molarity. So with molarity, the solution volume can change with temperature. Well, this place downtown or down by the river, they're working outside. They've got these huge vats that, that are outside. It's an industrial thing. If you go over the Crosby Willard Bridge and look towards town, you'll see that industrial plant there. Or if you go on the bike trails, there's a bike path that goes right past the place too. Anyway, they're dealing with this. And I mean, think about Wisconsin, our weather. You have days where it's 95, close to 100 degrees Fahrenheit. And you've got other days where we're down to minus 20 degrees Fahrenheit. So that's a huge swing in temperature that these people are working at. That's going to change their concentration of their stuff. And I mean, this stuff has to be spot on when they send it out. So my guess is they're probably working more in molality than they are molarity. Okay. Molality is not temperature dependent. It has to do with mass, and mass doesn't change with temperature. Density does, volume does, but mass does not. So here, they're going to be going with moles of solute divided by kilograms. Now, this is the kicker, okay? In all the other ones that we've done, this bottom thing has been what? Solution. Now it's solvent. Okay, so you got to be careful with this. So first of all, we are adding in 4.5 grams of sodium chloride. So I've got to convert that into moles. I'm going to divide by the molar mass. So 4.5, 58.5. So that ends up being 0.0769. That's moles of NaCl. I'm going to divide that. Now this gave me grams. So remember that you have 1 kilogram equals 1,000 grams. So I've got to take this and move my decimal 3 spots. So that's going to be 0.1 kilograms. Okay. Divided by 0.1, that's going to give me 0.769. Now, my unit for this, up here for molarity, it was a capital M. For molality, it's a lowercase m.
That's a weird name.
Molality. You don't use this at all in AP Chem. Just molarity. So as long as you can do molarity, but you do a lot of molarity in AP Chem. Right, Austin? A lot of molarity in AP Chem.
Yes.
Lots and lots. All right. I don't mess around with these subscripts like this. I'll show you how I do them. All right. I don't do that. Don't do that. All right. So here is part over the whole. Moles of solute divided by moles of solution. Okay. Part over the whole. We have 36.5% HCl divided by 62.5% H2O. They want to calculate the mole fraction. So just like when we did percent comp, 35.5%, we make it into grams, right? We change that. We assume that we have a 100-gram sample and we make it into grams. So then I'm going to take HCl. I'm going to turn it into moles. And then I'm going to take my water. That's 3.47 moles. Then I do part over the whole. Calculate the mole fraction for the solute and the solvent. So the mole fraction for the solute is going to be X And then I'm going to put HCl down here instead of the X and the Y. Didn't they have X and Y's up here?
A and B.
Yeah, that's what they did. A and B. Yeah, you're right. So I do HCl here. That's going to be my 1 mole of this divided by what? 4.47. I have to add these two things together to get my bottom number. And I end up with 0.224. It's unitless because my moles would have canceled. And that's going to be, so that's my HCl. And then this is going to be my H2O. This is going to be my 3.47 divided by 4.47. Or I could just take this and do what with it? Subtract it from 1. Yep. If I just have 2 parts, or you have 1 remaining part, you can do that for the last part, and you should come up with the same answer. Because this minus 1 will give you that. And that's mole fraction. And I like this. Some places, some people do the A and the B, but then you have to go, okay, which one's a solvent? Which one's a solvent? I don't remember. And so this is easier just to die. And I think it's easier for your brain too to go, okay, yeah, that's the HCl. You don't have to convert that back. Okay, A was the solute, so A is HCl. It takes that jump out of it. So I think it's much easier to do it this way. I think that's it for the notes, right? Yeah. Okay. So tonight's homework, and I haven't updated the board over there, my apologies, is 14.2. My guess is you've got about 10 minutes. You could probably come close to getting it finished before you even leave. I do have my answer key up front if you are working on it and you want to check your answers as you go through.